Hello everybody and welcome to our 5.3 concept video. In this section, instead of focusing on a application of integrals, we're instead going to look at a special type of integral called an improper integral. Don't worry, we'll still talk about an application when we're done, but in order for us to understand that application, we need to understand what it means for an integral to be improper. So if I have a definite integral bounded from a to b, of some function f of x dx, and I'm going to let L represent the value of this integral. An integral becomes improper as soon as we introduce infinity into this. And that can happen in three ways. So an improper integral is if we we could let the lower bound be negative infinity, meaning we could start with an infinitely small number or an infinitely negative number. Or we could do the opposite. Let our upper bound be an infinitely positive number. If either or both of those are happening, we have an improper integral. We could also have the case where the value of the integral ends up being infinite. If any of these cases are true, we're working with an improper integral. So let me give you a quick example of this. If you take the integral of 1 over x from 0 to 1, notice I didn't make either of my bounds infinite. But if you try and integrate this, you end up getting an infinite value or an undefined value. Why? The antiderivative of 1 over x is natural log. And if you bound this from natural log of 1 to natural log of 0, natural log of 0 is undefined. It gives you an infinite value out of it. We can actually see this by drawing a graph. The graph of 1 over x looks something like this. So if I'm trying to find the area from 0 to 1, that area just keeps going, giving me an infinite area. So we actually have a name for this situation. If the value of your integral is an infinite value, we say the integral diverges. But that's not the only way that we could have an improper integral. We could have an improper integral by just making one of my bounds infinite. And you may see an integral like this and say, oh, well then of course the value of the integral will also equal some infinite value, right? If I let my bound go off to infinity, then theoretically the area under that should also be infinite. Well, not so fast. That's true in some cases, but in other cases, it's not true. We can actually end up with a finite area even having infinite bounds. If that doesn't make sense, let me give you an example to kind of help with this. Pretend you're facing a wall. There is a finite distance between you and that wall, and yet you could theoretically take an infinite number of steps closer to that wall. How? By just taking smaller and smaller steps each time. A cool way to think about it is, could you take one step to go half the distance? Well, you're slowly getting closer to that wall, but if I'm only going half the distance, then I will never actually reach the wall. I'll take an infinite number of steps without ever reaching the wall, even though I'm working with a finite distance. So you'll see some examples on the homework where, even though you have an infinite bound, the value of the integral exists and isn't infinite. It's finite. So the way this works actually mathematically is what might happen is when you integrate your function and plug in infinity, it might end up in the denominator. And from what we've learned in chapter 1 with limits, what is this equivalent to? If your denominator is getting infinitely large, then your number as a whole is approaching 0. This is equivalent to 0. So even though I plugged in infinity, I got a finite value out of it. The same is true for an exponential decay function. If you plug in infinity, an exponential decay function gets infinitely close to 0 as you let x get infinitely large. And so this will also approach 0. Even though you're plugging infinity in for x, you end up with a finite value. So you'll see both of those examples as you work through some of these. To help with this, let's look at an application of this. Let's go back to my continuous income streams from 5.2. You're investing money, but you're continually adding to that investment every year. Well, what if we were to make this perpetual? What does that word perpetual means? Meaning we're going to let it go on forever. What if instead of having a fixed amount of time that we do this for, we say, okay, no, I'm going to add this amount to my account every year forever, from now on, till the end of time. This would be considered a perpetual continuous income stream. And the question becomes, can I calculate future value and can I calculate present value? Now, for the sake of simplicity, once again, we're going to assume that this continuous income stream is not changing. We're keeping it the same. Therefore, it's just going to be some constant R over K. Future value is e to the K capital T minus 1. And then my present value formula is very similar. So notice what happens when I make this perpetual. If I make it perpetual, then what is T? Well, I don't have a fixed amount of time anymore. Instead, I'm letting this happen perpetually. I'm letting it go on forever, meaning this value that I'm going to plug in for T is really just infinity. I'm plugging in an infinitely large number in for T because I'm letting this go on forever. Well, notice what happens with future value. If I plug in infinity for my future value into my future value formula, I get e to the K times infinity minus 1. Well, what is K? What is your interest rate multiplied by an infinitely large value? It stays infinitely large. And what is e to an infinitely large value? Since that's a growth function, that's also equal to infinity. Well, what's infinity minus 1? That minus 1's not going to do a single thing, so that minus 1, I can kind of ignore that minus 1. What is r divided by k multiplied by an infinite value? It's infinite. So if I try and do this with my future value, I end up with just an infinite value. And if you think about it, that makes sense. Because if I'm letting it go on for an infinite amount of time, how can I possibly figure out the future value if there is no set time where I'll stop? So this is impossible, or this diverges. But take a look at present value. If I try this again with present value, I get 1 minus e to the negative k times infinity. Well, like we just talked about earlier, because present value is dependent on a decay function, exponential decay function, I get this e to the negative infinity. If I have a decay function and I go and I let x get infinitely large, this just approaches 0. And therefore I'm left with r over k multiplied by 1 minus 0, which is just 1, or just r over k. So it turns out that present value, you can actually calculate the present value for a perpetual income stream. And it's as simple as r over k. So even though the integration here is behind the scenes, so this still kind of counts as an improper integral. So even though I was working with an integral with an infinite bound, I was letting it go all the way to positive infinity, I was still able to come up with a finite value for it. Because when I plugged in the infinity, the function made it go to 0. So you'll see plenty of examples as you go through the homework where even though it's an improper integral, the function will converge. You'll get an actual value for it. So go ahead and try some of these out. See what you can do. And if you get stuck, I'll be going over 2 problems from the homework in our examples video. Good luck, and see you next time.